Hello everybody, welcome to another edition of ANSYS from scratch, and today we'll be looking at the simulation of a Trombe wall using varying solar radiation data. Alright, let's get started. So the first thing we are going to do is start up ANSYS Fluent. Okay, then we have to draw a geometry. Okay, new space clean geometry. So ANSYS has two geometry software packages embedded into it. The first one is Space Claim and the second one is Design Modeler. I prefer working with Space Claim for some projects because Space Claim is easier to use and it's a lot better looking than Design Modeler. Okay, Space Claim is all started up. So the first thing we need to do is select our plane. So we need to make sure we're working on the correct plane. If not, the orientation of our geometry will be wrong. So we'll be using a two-dimensional geometry to represent a cross-section of our room with a Trombe wall. And to do this, we'll have to select the Z-axis and click. So once we select that, select new sketch plane. Select Z-axis, then view. Alright, okay, so once we do that, we're going to grab our rectangle tool, then draw a rectangle. So let's make it 30 by 3000 by 3000. Okay, so that's like 3 meters, a 3 meter wide room. It's not that much, but I think it's okay. So to move your object around, you hold the Control key on your keyboard and you press down on your mouse scroll wheel to enter the pan tool. So to zoom out, you just scroll up on your mouse scroll wheel. Okay, so that's that. So we'll draw another rectangle inside to represent the Trombe wall itself. So this is the room, this is the wall. So we'll have to cut this out to make sure that it doesn't affect our simulation. So the geometry essentially is the air domain, is the geometry of the air domain alone, and the air does not pass through the Trombe wall itself, so it will have to be cut out. So to do that, we go to split, then we select this, then we can press delete. Alright, so we're done with our geometry. So we go back to workbench, our geometry is all loaded up, then we can now open the meshing. Alright, our meshing environment is ready. So the first thing we need to do now, we can just do a test mesh. Go to home, mesh, generate. Let's just do a quick meshing to see what ANSYS can turn up. Okay, that is really poor. The element sizes are too large. In case you're wondering, these boxes are the elements. So we need to reduce that element size now. So this is 0.2 meters, we'll take that to 0.01 meters. Okay, alright, so once that is done, we'll click generate. Alright, the mesh has been generated and this is really good. You can see how fine the elements are. Okay, so if you want to check your mesh quality, you can just scroll down, statistics. Okay, so we have about 80,000 nodes and 80,000 elements. This is nice. Okay, so we'll have mesh update. Okay, so before we leave the meshing platform, we have to name our boundaries. If we don't name our boundaries, everything will be all confusing when we're setting the boundary condition. So we'll go to face selection. So we have no body, so we don't use body selection for this. We're just dealing with a two-dimensional geometry, so we have only faces and edges. Okay, so this will be our air domain. Okay, so we now name the edges now. Right click, create name selection. This should be our glazing. So the next one is our room wall. So to select all these faces at once, you hold Control and click each of them. We'll be applying similar boundary conditions to all three at the same time, so there's no need separating them. This is our room wall, and the same thing goes for the Trombe wall. Since it's the same object, we can treat it as one extended surface, and most importantly, since it's the same boundary condition. Okay, so we can check out our name selections here: air domain, glazing, room wall, Trombe. Alright, home, mesh, update. Alright, so this is a green light, we're good to go. So the next thing is the setup now. So we'll use double precision serial. Since it's a two-dimensional simulation, we need to get as accurate as possible. So we'll turn on double precision and we'll use serial processing. Personally, I prefer serial because parallel processing doesn't really have the ability to solve all simulation problems on ANSYS. It has its own limitations, but serial, it's more stable from my experience. So when you enter user-defined functions, you have problems using parallel processing. Okay, it's all loaded up. So the first thing we need to do is to set this time to transient. That's because we'll be using a solar radiation table. If we weren't using that and we want a steady state simulation, we'll just set it to steady, but we're using transient. So the gravity now will be in the minus y, the negative y direction, and have a value of 9.81. Okay, so we're done with this. That's in general. So models now. Which models are we using? Definitely we're using the energy equation. Viscous, we can leave it as laminar since it's a two-dimensional geometry. Radiation, let's use discrete ordinates. Okay, that's all for the model. So materials now. So here we'll be defining the material properties of the Trombe wall. So to edit our material properties, we just go to create or edit. So we'll click on change or create now. Okay, so we impute the properties for glass. I already have that got from online sources. So the chemical formula GL, material type solid, we can leave this. So this is 2220, specificate 800, thermal conductivity 0.8. I think we can leave all these ones. So change or create, overwrite aluminium, yes. We need another one, which is brick wall. Brick wall. So we'll call that brick wall. So the density of the wall is 1700, thermal conductivity 1.65, and the specific heat capacity is 940. Overwrite glass, no. So it will create a copy there. So if you click no, it creates a copy. If you click yes, it overwrites. So we can close. So we can now check out the property of air now. So density, we don't want a constant density. We'll just leave it as an ideal gas. Okay, to close now. So let's check our fluid zones, our cell zone condition. So our air domain, we need to make sure it's in the right place. So the material name is air. Okay, yeah, okay. So the type is fluid, so we're good to go. So boundary conditions, one of the most important sections. We need to organize it by zone type. That way we'll see everything perfectly. So for our boundary conditions, our glazing now, we'll be using our solar radiation data. Okay, so let me just show you something quick. So we need to put a user-defined function, but it's not here. So that's what we're quickly going to grab now. So to do that, we need to prepare the table. So what I have is a radiation table I called testrad2. This first row is the header file. It gives ANSYS instructions on the name of the file, the number of columns, the number of rows, and whether it repeats or not, or whether it's an oscillatory motion. This is the title of this column, title of this column. So you can get it and use it as a template. You can work for velocity, temperature, or as you know, solar radiation. Okay, so something you need to know, this value here must be the number of rows. If not, your ANSYS software will crash. You have to start your project all over again. That's, I think it's a bug or something like that, but the header file must accurately describe what is in the table. If not, Fluent will simply crash and you wouldn't know why it crashed. So debugging will now be a big issue for you. So make sure you get your header file right. 2 columns, 9 rows, doesn't repeat. Alright, so the next thing is the format we need to save this header file as. We need to save it as a .prof file, and we need to save it in the correct directory. So 2 things you need to note: the file format and where you're saving it. So it will be testrad2.prof. okay, so this is a profile file. We save it in the main file, Fluent. Okay, so it has to be saved inside this directory. Let me show you again. dp0, this is your simulation directory. You go to the major one, dp0 fff fluent, then is here you're to save it. Save. Alright, so once that's done, we can go back to Fluent, then load it. So to load it, we just have to use the following command line codes: file, then read /transient table. Okay, then we impute the file name test-rad2.prof. don't forget. Alright, so it's loaded up. So if the header file is not correct, you have problems here and your whole Fluent software will crash. Okay, so we can now go back to glazing, heat flux. Yeah, testrad is available for use. So the material name is glass. Radiation now, boundary conditions. So we have testrad here. Let's make this testrad this, so it's mixed. So the next is the room wall. So we can just simply treat the room as an adiabatic wall. So we select the material to brick wall and the heat flux to 0. In ANSYS, to set a boundary condition to be adiabatic, what you use is heat flux of 0. Okay, that's the way we do it in ANSYS. Okay, so Trombe wall now, we put the same thing. But the Trombe wall won't be adiabatic, it will be at room temperature. Alright, and the material property will be the brick wall. again. So boundary, we're done with the boundary conditions now. So another interesting thing to do is to create monitors. Monitors will help you log specific parameters of interest during your simulation. So let's go to report definitions, new surface report. Since we're using a two-dimensional geometry, it has to be a surface report and an area weighted average. So we will log the air temperature. Okay, so this is temperature, total temperature of the interior air domain. Then we need to create a report plot. Okay, so if we want to monitor specific points such as the temperature of the upper air vent and the temperature of the lower air vent separately, we have to create points which will tell ANSYS that we need to log these specific points. Okay, so we create point. Alright, so select point with mouse, then we go to where we want to monitor and right click. Take note, right click. So we can see it has appeared there. We now name it to the upper air vent. Create. Okay, so I'd like to log the back. Okay, I'd like to log the lower air vent now. So I'll just simply scroll there, select point with mouse, right click, call it lower air vent, create. Okay, so we're done, close. So now we'll go back to report definitions. So new surface report, area weighted average. So as we can see, our upper air vent and lower air vent points have appeared for us to monitor parameters at those points. So we have upper air vent temp. So upper air vent temperature, total temperature, create report plot. Okay, new surface report, area weighted average, lower air vent temp. So that's lower air vent. Temperature report plot. Okay, so I also like to log the glazing temperature. Surface reports, area weighted average. Okay, so we can create a report file in ANSYS for use in Excel. Okay, so we can tell ANSYS, I want to log these data points and I want to use them later in Microsoft Excel. To do that, we go to monitors, report files now. Okay, so you set the things you want to save for later during the simulation. So I want to save the upper air vent, lower air vent, glazing, air temperature. So add. So flow time is already there. So I usually rename this to important simulation files. Okay, so you find that in the same directory as your radiation table. So if we want to create custom report plots, create new. Once you add a variable, other variables that do not have the same unit will disappear. Take note of that. So you can only create plots of variables that have the same unit. So plot title will be comparison plot. I'm not a fan of spaces in ANSYS. Okay. So we need to save every one time step. If you don't do this, you wouldn't be able to have files for post-processing later on. The run calculation. First of all, we need to initialize. Okay, so run calculation. So time step size, we'll do it for 1800 seconds. That's like 30 minutes, and we'll do it 9 times. 20 is okay. So before that, I would love to change the residuals here. 0.001. These are the convergence criteria I'm changing. We're relaxing it a lot so that our simulation will be completed before it goes on to the next time step, so that we ensure that the simulation was performed properly. So run calculation, calculate. Our simulation is all done, and let's just take a look at our plots. This is a nice simulation. This is our air temperature, upper air vent, lower air vent, the glazing. We can see the temperature with which it's peaked at. Then this is the comparison. And go over to CFD post. Alright, CFD post is all loaded up, so we just need to view symmetry. Okay, so we right click, insert contour of sample. So this will be our room temperature. So our contours of temperature, range, user specified. Let's look at 300, so like 325. Okay. Wow, this is really nice. You can see most of the hot air is above, while the cooler air comes down below. So if we want to change our time step, let's look at a quick animation now. Time step animation. So that's it for now. Be sure to subscribe and check out my other videos. Till next time, this is ANSYS from scratch.